While you sit in your room right now, 4,000 light years away across the silent ocean of space, a massive sun is flickering like a broken lamp. Something so large that it defies basic physics is moving across its burning surface, blocking out huge chunks of light without leaving a trace. Astronomers are sitting at their glowing screens in total disbelief as a massive cosmic shadow slides across the sky. Whatever is creating this shadow is far too large to be a planet and far too strange to be a simple cloud of dust. If you want to explore the deepest mysteries of our universe with real scientific facts, hit the subscribe button right now. Joining our community ensures you will always be the first to hear about these mind-bending discoveries before anyone else. To truly understand why this single distant star is causing so much confusion across the scientific world, we have to look at how astronomers usually discover new worlds. For many decades, scientists had no direct way of taking clear photos of planets orbiting other suns. These distant worlds are simply too far away, and the bright glare from their parent stars completely washes them out. To solve this giant problem, astronomers came up with an ingenious technique known as the transit method. The transit method works on a remarkably simple idea that anyone can easily picture in their mind. Imagine placing a very bright light bulb on one side of a large dark room and watching it from the far wall. If a tiny fly flies directly in front of that light bulb, it will block a tiny fraction of the light reaching your eyes. You might not be able to see the body of the fly itself, but if you measure the light with a precise sensor, you will notice a tiny, brief drop in overall brightness. In deep space, stars act like those massive light bulbs, and orbiting planets act like those small, passing bugs. When a planet's orbit aligns perfectly with our line of sight from Earth, the planet crosses in front of the star once every orbit. Astronomers call this crossing event a transit. As the planet glides across the fiery face of its star, it casts a tiny shadow out into the cosmos toward our space telescopes. By recording these light changes over time, scientists can map out the entire planetary system. When a standard planet transits a normal star, it creates a very specific pattern on a computer graph. Astronomers measure the brightness of the star over time and plot those numbers on a visual chart called a light curve. A standard light curve shows a perfectly straight, flat line as long as the star is shining normally into empty space. The moment a planet begins to cross the edge of the star, the light curve drops down smoothly in a clean, symmetrical U-shape. This U-shape happens because the planet takes time to move onto the star, glides across the middle at a steady speed, and then takes time to exit the other side. The depth of that light curve drop tells scientists exactly how large the planet is compared to its parent star. A massive gas planet like Jupiter, which is about 11 times wider than planet Earth, will block roughly 1% of a normal sun-like star's light. A smaller world like Earth blocks only a tiny fraction of a single percent. Because planets follow strict gravitational paths, these light drops repeat on a precise and predictable schedule. If a planet takes 300 days to complete one full orbit around its star, the light drop will happen every 300 days without fail. The drop will always last the exact same number of hours, and the starlight will always fall by the exact same depth every single time. This steady, repeating rhythm allows scientists to confirm that a real planet exists without any doubt. For several decades, this reliable method allowed humanity to discover thousands of distant exoplanets across our Milky Way galaxy. In the year 2009, NASA launched a powerful space observatory called the Kepler Space Telescope to automate this search on an unprecedented scale. Kepler was placed into orbit around the Sun, far above Earth's muddy atmosphere, and pointed continuously at a single patch of sky in the constellation Cygnus. For 4 full years without stopping, Kepler monitored the exact brightness of over 150,000 stars at once. The amount of information gathered by the Kepler Space Telescope was so vast that human scientists could not possibly check every chart by hand. Advanced computer algorithms were created to scan through millions of light curve graphs automatically, searching for those smooth, repeating U-shaped dips. Whenever the computer detected 3 identical dips happening at equal time intervals, it flagged that star as a candidate for a new planetary system. Everything in our astronomical surveys seemed organized, predictable, and fully explained by established physical laws. However, computer algorithms are only as smart as the programming rules created by their human engineers. Because the automated software was specifically programmed to search for smooth, symmetrical, and perfectly repeating dips, it was completely blind to light patterns that were irregular or chaotic. If a star experienced strange light drops that did not repeat on a regular schedule, the computer program would ignore the data, assuming it was just random background noise or instrument glitch. To prevent important scientific discoveries from slipping through the cracks, researchers created a public project called Planet Hunters. The Planet Hunters initiative allowed over 300,000 ordinary citizen volunteers from all around the world to log onto a website and examine Kepler light curves using their own eyes. Human brains are exceptionally good at spotting subtle visual patterns that simple computer codes might miss entirely. Volunteers were asked to look at raw starlight graphs and draw boxes around any suspicious dips that looked unusual. In the year 2011, several volunteer researchers flagged a light chart belonging to an otherwise ordinary star designated as KIC 8462852. Have you ever participated in a citizen science project or analyzed real satellite data from your own home computer? Tell us about your experiences in the comments section below, and like this video to support open public research. The star known as KIC 8462852 is an F-type main sequence star located roughly 1,400 light-years away from Earth in the Cygnus constellation. It is about 50% larger and significantly hotter than our own Sun, shining with a bright, steady white glow. Under normal circumstances, a star of this specific type should be completely stable, exhibiting almost no noticeable changes in brightness over human timescales. Yet, when astronomers looked closely at the light charts flagged by the Planet Hunters volunteers, they were absolutely stunned by what they saw. Instead of the neat, tiny 1% drops caused by normal worlds, KIC 8462852 was experiencing wild, irregular plunges in light that made no logical sense. During one event in the year 2011, the star's overall brightness suddenly crashed down by an incredible 15%. A drop that huge was completely unheard of in the history of stellar astronomy. To cause a 15% light drop, an object would need to be hundreds of times larger than planet Earth, spanning millions of miles across open space. Even more shocking details emerged as scientists continued to examine the raw observational records. 2 years after that initial event, the star experienced another series of massive light plunges that lasted for several weeks. During this second complex event, the star's light plummeted by an astounding 22%. That is more than 20 times larger than the shadow cast by Jupiter, the largest planet in our solar system. Whatever was passing in front of this distant sun was vast enough to block nearly a quarter of its total light output. Furthermore, the shape of these light drops completely violated the standard rules of planetary motion. Instead of a clean, symmetrical U shape with smooth edges, the light curve for KIC 8462852 showed jagged, asymmetrical cliffs. The star's light would drop slowly over several days, stay faint for an unpredictable period, plunge sharply downward again, and then jump back up to full brightness in a matter of hours. The light curve looked like the outline of a jagged mountain range, rather than a smooth planetary shadow. When team members first saw these incredible numbers on their computer screens, their instant reaction was complete skepticism. In science, extraordinary claims require extraordinary evidence, and the researchers assumed the telescope hardware must have suffered a sudden failure. They hypothesized that a high-energy cosmic ray might have struck the telescope sensor, or that a software glitch had corrupted the light file during data transmission back to Earth. Engineers conducted exhaustive diagnostic tests on the Kepler hardware, recalibrated the software routines, and reprocessed the raw observational files. After months of rigorous testing, the engineering teams confirmed that the Kepler Space Telescope was functioning in perfect health. The unusual light dips were not caused by instrument dust, sensor corruption, or electronic noise. The data was completely clean and accurate, meaning that an object or collection of objects of incomprehensible size was truly out there in deep space, blocking 22% of the starlight. Humanity was officially staring at a completely new cosmic phenomenon that no textbook had ever predicted. Do you think a single giant object could cast a shadow that large? Or are we looking at a massive collection of smaller items moving together? Share your personal theories in the comments below, and subscribe if you want to follow every step of this ongoing investigation. News of this incredible stellar anomaly spread like wildfire throughout the international scientific community. The lead researcher who directed the initial study, Dr. Tabitha Boyajian, published a comprehensive paper documenting the weird findings, and the object was quickly given the informal nickname Tabby's star. Telescopes across the world, from massive professional observatories in Hawaii to small backyard setups owned by dedicated amateurs, were immediately pointed toward the Cygnus constellation. Everyone was desperate to catch Tabby's star in the middle of another active dimming episode. What made studying Tabby's star exceptionally difficult was the complete absence of any repeating schedule. Standard exoplanets move in fixed orbital paths governed by Kepler's laws of planetary motion, allowing scientists to calculate exact schedules for future transits down to the exact second. Tabby's star, on the other hand, dimmed at completely unpredictable intervals. Months or even years would pass with the star shining at total stability, followed by sudden, chaotic dimming events that appeared out of nowhere without any warning signals. To explain these wild light drops using natural physics, scientists began generating testable hypotheses. The first major natural theory proposed by astronomers was the giant comet swarm hypothesis. If a massive icy body or a small planet had recently suffered a catastrophic collision with another large object in that star system, it could have shattered into thousands of giant comets. As these comets swung close to the host star, the intense stellar heat would evaporate their frozen surfaces, creating gigantic clouds of dust and gas that trailed behind them. In theory, if a dense cluster of giant comets swept in front of the star along an elongated orbit, those massive dust clouds could block large amounts of starlight. Because comet clouds are uneven, ragged, and spread out across millions of miles, they could create the chaotic, asymmetrical dips observed in the Kepler light curves. This theory seemed plausible at first glance because comets are common objects in planetary systems, and their dusty tails naturally create irregular shapes that do not look like solid spheres. However, as soon as astrophysicists ran detailed computer simulations to test the math behind the comet model, severe problems began to emerge. To cause a light drop of 22%, the system would require a cluster of over 30,000 massive comets, each several miles wide, all moving together in a tight formation. Furthermore, all those thousands of comets would have to pass directly in front of the star at the exact same moment during Kepler's brief observation window. The statistical probability of such a rare event happening right when humans were looking was remarkably close to zero. An even larger physical flaw with the comet theory involved basic thermodynamic laws regarding heat radiation. When icy comets and heavy dust clouds pass close to a hot star, they absorb immense amounts of high-energy starlight. According to basic thermal physics, that absorbed energy cannot simply vanish into nothingness. The dust must heat up and re-radiate that energy back out into space in the form of longer infrared wavelengths, which human instruments detect as thermal heat radiation. If Tabby's star was surrounded by a massive swarm of 30,000 comets and heavy dust clouds, the entire system should have been glowing brilliantly in infrared light. Scientists immediately pointed NASA's powerful Spitzer Space Telescope and the Wide-Field Infrared Survey Explorer, known as the WISE satellite, directly at the star system to measure its thermal output. If the dust was present, the infrared sensors would easily pick up the heavy heat signatures radiating from the surrounding debris disk. When the thermal readings came back from the infrared space observatories, astronomers were met with another perplexing puzzle. There was almost no excess infrared radiation coming from the Tabby's star system whatsoever. The star showed only the normal baseline heat levels expected from a single bare stellar furnace with no surrounding dust disk. This critical observation meant that whatever object was blocking 22% of the starlight was somehow staying icy cold, or it was made of a material that did not release heat like natural space dust. If you were a scientist working on this project, how would you test a space object that blocks light but radiates almost no heat into space? Write your ideas in the comments section below and subscribe to keep discovering how researchers solve these deep cosmic riddles. With every standard natural explanation hitting a dead end, an astrophysicist named Dr. Jason Wright published a controversial paper proposing an extraordinary alternative. He pointed out that the chaotic, asymmetrical light curve of Tabby's star matched theoretical models created for massive artificial structures. In the year 1960, a famous physicist named Freeman Dyson proposed that an advanced alien civilization might eventually outgrow the energy resources of its home planet. To survive, such a species might build a vast network of gigantic solar collectors orbiting their home sun to capture its energy output. In science fiction and theoretical physics, this hypothetical megastructure is known as a Dyson Swarm. A Dyson Swarm would not be a solid, rigid shell surrounding a star, as that would be structurally unstable against gravity. Instead, it would consist of millions of independent, city-sized solar panels, habitats, and energy collectors orbiting the star in various complex planes. As these massive artificial structures crossed in front of the star from Earth's line of sight, they would block huge amounts of starlight in irregular, non-repeating patterns. Because artificial panels could be engineered to redirect thermal radiation or harvest energy with extreme efficiency, they might not emit the heavy, uniform infrared heat that natural dust clouds release. For a brief moment in scientific history, mainstream astronomers acknowledged that while an alien megastructure was the least likely explanation, it could not be ruled out immediately because all proposed natural models were failing to fit the observational data. The mystery transformed overnight from an obscure academic debate into a global headline story. The possibility of detecting an advanced extraterrestrial intelligence prompted scientists at the SETI Institute to take immediate action. Researchers pointed the massive Allen Telescope Array, located in California, and the world-renowned Green Bank Telescope, situated in West Virginia, directly at Tabby's star. These ultra-sensitive radio observatories scanned millions of distinct radio channels across several months, searching for non-natural radio pulses, narrowband signals, or powerful laser transmissions that might indicate technology. Radio astronomers listened intently across broad spectrums, hoping to catch a faint signal generated by artificial machinery or interspace communications within that distant star system. After hundreds of hours of continuous observation and complex signal analysis, the radio searches came up completely empty, The instruments recorded only the silent, random static noise of natural background space. While this empty result did not disprove the existence of technology, it provided zero evidence to support the artificial megastructure claim. While the radio searches came up quiet, another astronomer made a discovery in historic records that deepened the mystery even further. An astrophysicist named Dr. Bradley Schaefer decided to investigate the long-term history of Tabby's star by analyzing historical astronomical archives. He traveled to Harvard University, which holds a world-famous collection of over 500,000 glass photographic plates that captured images of the night sky continuously from the late 1800s to the late 1900s. Dr. Schaefer meticulously analyzed over 800 historic photographic plates that recorded Tabby's star between the years 1890 and 1989. By carefully measuring the exact size and density of the star's tiny chemical dots on these glass plates across a full century, he calculated the star's overall baseline brightness history. What he discovered was a secondary long-term trend that left astronomers thoroughly bewildered. In addition to the sudden, sharp dips in light lasting a few days, Tabby's star was also slowly and continuously fading away over long time scales. Between 1890 and 1989, the total brightness of Tabby's star had steadily dropped by approximately 14%. A normal mature star like our Sun should remain at a totally constant brightness level for billions of years, without fading by even a tiny fraction of a percent over a single century. Something out in that distant system was actively choking off the star's light over generations. Initial reactions to Schaefer's historic discovery were met with skepticism, as critics suggested that old photographic glass plates from the 19th century might have degraded unevenly over time. To verify whether this long-term century dimming was real, scientists re-examined the high-precision modern digital data gathered by the Kepler Space Telescope during its 4 years of operation. Two astronomers named Benjamin Monte and Joshua Simon performed an independent, ultra-precise analysis of every raw pixel recorded by Kepler. Their findings fully confirm the historic Harvard trend. During the 4 years that Kepler observed Tabby's star, the star's baseline light dropped smoothly by an additional 3% overall, on top of the sudden massive dips. This proved beyond all doubt that the century-long fading was a genuine physical event happening in deep space, not an error caused by old photographic glass. Astronomers were now forced to explain two completely different types of dimming occurring simultaneously: rapid, chaotic plunges and a slow, continuous fading. What do you think could cause a massive star to steadily lose 3% of its brightness in just 4 years, while also experiencing sharp plunges? Share your thoughts in the comments below, and hit the like button if you are amazed by how complex deep space can be. The crucial turning point in this mystery finally arrived in May of the year 2017, when Tabby's star began its first major dimming episode since the end of the Kepler mission. Thanks to automated warning networks, hundreds of professional and amateur observatories around the world were alerted within minutes. Telescopes across Earth immediately pointed their mirrors at the star, observing the dip simultaneously across multiple wavelengths of light, including ultraviolet, visible, and infrared spectra. Observing a dimming event in multiple colors at the exact same second provided the ultimate scientific test to determine the physical nature of the blocking material. If the object blocking the starlight was a solid, opaque body, such as an alien solar panel, a planet, or a giant moon, it would block all colors of light equally. A solid piece of rock or metal acts like a total barrier, blocking blue light, red light, and infrared light with identical efficiency, creating a completely neutral shadow. However, if the blocking material was composed of microscopic particles, such as fine dust or smoke, it would interact with starlight differently depending on the wavelength of the light. Tiny dust particles scatter short, blue wavelengths of light much more effectively than longer, red wavelengths. This physical process, known as Rayleigh scattering, is the exact same reason Earth's sky appears blue during the day and red during sunset. If the shadow was caused by fine dust, the star would appear significantly redder as it dimmed. When the multicolored observation data from the May 2017 dip was processed, the result was completely decisive. The star lost significantly more short-wavelength blue light than long-wavelength red light as it faded. This clear color signature provided undeniable proof that the object passing in front of Tabby's star was not a solid alien megastructure, a giant planet, or massive metallic shield. The blocking material was definitively made of fine dust particles, each one smaller than a single micrometer across. While this multi-wavelength discovery conclusively ruled out solid artificial megastructures, it opened up a whole new set of complex scientific questions. Where could such an astonishing, seemingly endless supply of microscopic dust possibly be coming from? In a stellar environment, fine dust cannot simply float around a star indefinitely. The intense outward pressure of the starlight itself, known as radiation pressure, acts like a relentless cosmic wind, pushing tiny dust particles completely out of the star system over brief timescales. To keep blocking starlight continuously over a century, Whatever process is creating the dust must be producing trillions of tons of fresh powder every single day. If the dust source stopped manufacturing new material, the star's radiation pressure would clean out the surrounding space within a few decades, restoring the star to full brightness. This means that right now, at this very second, an extremely violent and active destruction process is occurring in that distant system, continually pulverizing immense amounts of matter into fine dust. To explain this continuous dust creation, astrophysicists developed a compelling theoretical model involving the dramatic destruction of an icy exomoon. Imagine a large gas giant planet, similar to Jupiter, orbiting Tabby's star, surrounded by a massive icy moon similar to Saturn's moon Titan or Jupiter's moon Europa. If the gas planet's orbit became gravitationally unstable, it could be pulled dangerously close to its host sun over millions of years. As the giant planet drifted inward, the star's immense gravity would create powerful tidal forces, gradually stripping the icy moon away from its parent planet. Once liberated, the moon would enter a highly elliptical, chaotic orbit that brought it extremely close to the burning surface of the star. During every close pass, the intense stellar heat would vaporize the moon's frozen crust, blasting huge plumes of gas and fine dust out into open space. Over time, these outer gas plumes would be pushed away by radiation pressure, leaving behind a dense trail of rocky dust grains wrapped around the star in a massive, uneven ring. As this dusty debris ring orbits the star, dense clumps of dust pass directly between Earth and the star, causing the sudden, steep plunges in brightness. Meanwhile, the finer dust particles spread out evenly along the entire orbital path, creating a thin, continuous shroud that causes the slow, century-long fading. Another fascinating theory proposed by theoretical astrophysicists involves a catastrophic collision between two planet-sized bodies. In the early history of our own solar system, 4.5 billion years ago, a planet the size of Mars smashed directly into the young Earth. That titanic crash ejected vast amounts of molten rock and debris into orbit, which eventually clumped together under gravity to form our moon. If a similar planetary collision recently occurred around Tabby's star, the impact would pulverize both worlds into billions of jagged fragments. This titanic collision would leave behind a chaotic, sprawling disk of fine dust and debris spanning millions of miles across the star system. As the larger planetary chunks collide with each other repeatedly inside the debris disk, they would continually grind each other down into microscopic dust, maintaining a fresh supply of powder to block the starlight. This giant smash-up model neatly explains the chaotic dips, the long-term fading, and the presence of fine dust particles detected during the 2017 multi-wavelength observations. Do you think Tabby's star is showing us the destruction of an icy moon or a collision between two planets? Write your vote in the comments section below, and subscribe to see which theory wins as new data comes in. To understand why a planet collision generates so much dust without releasing massive heat, we have to look closely at the physics of rock crushing. When two massive worlds smash together at thousands of miles per hour, the energy of the impact is so extreme that it vaporizes millions of tons of solid rock instantly. This vaporized rock expands outward into the freezing vacuum of space, where it cools down with incredible speed, turning from glowing gas directly into tiny solid mineral crystals. These mineral crystals form a microscopic smoke ring that expands across the entire star system over several decades. Because these particles are spaced extremely far apart across millions of miles, they do not touch each other or trap heat inside a dense ball. Instead, each individual dust particle radiates its heat away into empty space almost instantly, remaining cold and dark while still blocking blue starlight from reaching Earth. This elegant physics model explains why our infrared space telescopes detected almost no excess heat signature around the star. What makes the story of Tabby's star even more thrilling is that it is no longer an isolated mystery in our astronomical catalogs. As modern automated sky surveys scan the sky night after night, astronomers have begun discovering other distant suns that exhibit similar chaotic dimming behaviors. A star designated as EPIC 2042 SET891X was observed undergoing sudden light drops of up to 65%, while another star named V928 Tau experienced sharp, unpredictable plunges that mimic the light curves of Tabby's star. An even more bizarre object discovered recently is HD 139139, nicknamed the Random Transitor. This star exhibited 28 separate, distinct dimming events over an 80-day observation window. However, unlike standard planetary transits, the timing between these 28 dips showed zero mathematical pattern whatsoever. It was as if someone was flipping a light switch on and off at completely random intervals, baffling astronomers who are still attempting to model its behavior. These extraordinary discoveries prove that Tabby's star is not just a single freak accident of nature, but rather the first known example of a whole new class of cosmic phenomena. They show that distant solar systems are far more dynamic, violent, and chaotic places than scientists ever imagined. Planetary systems do not always settle down into quiet, permanent stability. Instead, entire worlds can be torn apart, ground into dust, and scattered across the void of space long after their initial formation. To unravel these complex systems, scientists are deploying humanity's most powerful space observatories, including the James Webb Space Telescope. With its massive gold-coated mirror and ultra-sensitive infrared spectrographs, James Webb can analyze the light passing through these distant dust clouds with unprecedented precision. By breaking the starlight down into detailed chemical signatures, researchers can identify the exact minerals present in the dust, determining whether we are looking at crushed silicates, iron, water ice, or complex organic compounds. Furthermore, upcoming ground-based observatories like the Vera Rubin Observatory in Chile will soon begin scanning the entire night sky every few nights with a giant 3-gigapixel camera. This revolutionary survey will monitor millions of stars simultaneously, likely discovering hundreds of new dipping stars across our galaxy. By studying a large population of these flickering suns, astronomers will be able to map out every stage of planetary destruction, from initial collision to ultimate dispersion. When we observe these flickering stars across our galaxy, we are getting a rare glimpse into the chaotic life cycles of planetary systems. In our own solar system, the planets move in near-perfect circles that have remained stable for billions of years, creating a safe, peaceful cradle for life. But across the wider Milky Way, gravitational interactions between giant planets can trigger unpredictable gravitational chaos, flinging smaller worlds out into space or sending them crashing directly into their parent suns. Studying these extreme cosmic events allows scientists to test how gravity behaves over massive scales and long time periods. Every new dipping star gives researchers a fresh laboratory to study how dust clouds expand, how radiation pressure cleans out stellar orbits, and how planetary debris alters starlight. Instead of relying on computer simulations alone, astronomers can watch real planetary destruction happening in real time across the cosmos. Connecting these distant events back to our own lives gives us a profound new perspective on our existence here on Earth. For over 4 billion years, our solar system has enjoyed a remarkably calm, stable environment, allowing delicate living organisms to thrive, evolve, and build human civilization. But studying stars like Tabby's star reminds us that planetary stability is a rare and precious gift, achieved in a cosmic ocean filled with relentless gravitational forces and violent smash-ups. When we look up at the night sky and observe the faint white light coming from Tabby's star, we are looking back in time through 1,400 years of space history. The photons hitting our telescope sensors tonight left that host sun during the early Middle Ages on Earth, traveling across quadrillions of miles of empty space, carrying the detailed physical record of a massive planetary catastrophe. We are privileged witnesses to a real-time chapter of cosmic evolution unfolding across the galaxy. As technology advances and our space instruments grow more sophisticated, we are rapidly closing in on the final answer to this incredible deep space mystery. Whether Tabby's star is being shrouded by an evaporating icy moon, a crushed planet, or a cosmic collision process we have not yet imagined, the search for truth demonstrates the boundless power of human curiosity and scientific exploration. If you are amazed by the deep mysteries of our universe and want to keep exploring the cosmos with us, please hit the subscribe button right now. Make sure to turn on all notifications so you never miss a new story. Drop a comment below telling us what you think is hiding around Tabby's star, and share this video with anyone who loves science. Thank you so much for watching, and we will see you in the next Deep Space investigation.